So exponential and logarithms, this chapter, exponentials and logarithms. And you had some of that in Algebra 2. But I would say more and more as the years go by. We teach less and less of that in Algebra 2. So more of this could be new to more of you than ever before. It starts with exponential. The first section is exponential. The second section is logarithms. It's where we just introduce those two kinds of functions. The third is properties of logarithms. The fourth is solving equations between logarithms and exponentials. And the thing is that because the nature of these functions, they happen to be inverses of each other, we use one to solve the other. That's why they're taught together, because you need them to solve each other. And then the last section out of the 5 is all word problem application stuff, because these are very practical kinds of functions. If you just turn back to the 5th section and look at some of the stuff that's in there, compound interest, population growth models, carbon dating and radioactive decay, bacteria growth. I mean, some of these things I know you've had in other classes, like half-lives, right? You do that in chemistry. You might have done population growth in a biology class that used at least some part of it was modeled with exponential functions. So these are very practical kind of things, and there will be some element of word problems and things like that when we go over it. So first day, we're just doing exponentials, and this part of it, at least part of it, you did get some of this in Algebra 2. A little bit different, but about not that much. Okay, by exponential function, we mean something that has the basic format of f of x equals a to the x. Okay, a is a constant, right? It's not a variable, it's a constant. Okay, a does not equal 1, because what kind of function would you have if you let a equal 1? 1 to the x is 1, right? 1 to any power is still 1, so that would be a constant function. So a cannot be 1, and it's defined as being positive. Right? And this is an exponential function because the variable is in the exponent. Right? That's what makes, you wouldn't say something like f of x equals x squared. That's not exponential because it has an exponent, but the variable's not in the exponent. Right? It's that variable up here. Right? That's what makes this exponential. Okay. Now, if you remember a little bit of this from Algebra 2 or prior years, you may remember that they defined exponential function like this. F of x equals a times b to the x. A little bit different. But we'll deal with if there happens to be a constant in front of that. And definitely we're calling the base of the exponential as a. They called it b. So again, this a is called the base. It's the base of the exponential. I should have written that. A is base. Okay, so what's the first thing we need to do when we look at a new function? Graph it. You got to know what's the shape of this thing. And in order to have something to graph, I need to fill in the a. So I filled in the a with a 2. So I graphed y equals 2 to the x. And you can see what the shape of the graph is. Right? What is this graph doing from left to right? It's increasing, right? So y equals 2 to the x is increasing from left to right. In fact, it's increasing quite rapidly past a certain point. Right? That's called exponential growth. Right? Exponential growth is very specific in mathematical terms. It means something like this. In non-mathematical terms, people could use in a non-math science related thing, if they talk about exponential growth, what do they mean? Grows really fast, right? It's something that's growing really fast. They may be using it incorrectly. It may not technically be exponential, but you know the point, right? That's what you say when you mean something is growing really, really fast. Right. So definitely we can say about this exponential growth model, there's a few things we could say about it, right? It's increasing, always increasing. What did it mean if a function is always increasing? Or another way to say it, would this pass a horizontal line test? Yeah, it would. And what did that mean when we learned about that? It has an inverse. Okay, it has an inverse. Because of the shape of the graph, it definitely has an inverse. Looking at this function here, right, is there any way, any value of x you could imagine we could plug in and get y to equal 0? I mean, what would happen if you plug in x equals 0? It would be 2 to the 0, but anything to the 0 is 1, right? Which is why you have a y-intercept of 1, right? Y-intercept. Another thing to note, 0, 1. Okay, but what that tells you is you see this graph getting really close to the x-axis there. It does not touch the x-axis. It cannot, because there's nothing you can do to make y equal 0, right? So there's the x-axis, y equals 0. So since this graph is approaching the x-axis but is never going to touch it, what do we call that line? It's an asymptote, right? So exponential has an asymptote. Exponential growth has an asymptote of y equals 0, which is the x-axis. Okay. Oh, I didn't know that. I wanted that. Okay, so now, what is the domain of this function? I mean, yeah, if you're looking at the graph, I mean, you can see the tilt of that line, right? It's going maybe ever so slowly, but it's still going to the right, and it's still going up. And it'll do that forever. So in terms of domain, it's clearly going infinitely to the left, and it's going infinitely to the right, so the domain is all real numbers, right? All reals. What is the range? Yeah, it starts in the middle, it goes up from there, and it actually does not touch the middle. So you're going to have to say y is greater than 0. Okay, let me see if I have any other notes I wanted to get out of that. Okay, note the asymptote, the y-intercept domain, range increasing. Okay, which means it has an inverse. Okay. So all that stuff is what we know about y equals 2 to the x, which is growth because the a is greater than 1. We call that exponential growth. All right. Now notice the difference between the graphs. I graphed 2 of them here. Here's our y is 2 to the x. It's the same one I had in the last, but I added y equals 4 to the x. It's still an exponential growth. I did change the base. It's a little bit different. Does it change much on the graph? I mean, this basic shape is still the same. The y-intercept is still 1. It still cannot touch the x-axis, so it has an asymptote at y equals 0. The domain is all real numbers. The range is y greater than 0. It's always increasing. So whatever the base is, as long as it's greater than 1, for us, it's for all practical purposes, pretty much the same. Okay, it doesn't the same. You know, if I had to sketch the graph of any of them, any exponential growth graph, I would probably just do something like this. And I wouldn't worry so much about the details. You know, is it really like that or is it like that? I mean, the main thing is get the important details are it has an asymptote there, it has a y-intercept of 1, things like that. The basic shape, right? We should understand that much about exponential growth. Shape approximately. The same. Right. Domain, range, asymptote, intercepts. Unchanged. just so it's written in the notes there. Okay, now let's see what happens when I graphed here. I've got y equals 2 to the x. And now I have multiplied by a constant in front of the 2 to the x. I multiplied it by 3. How does that change the graph? It changed the y-intercept, right? It multiplied it by 3. Again, how do you find the y-intercept? You substitute x equals 0, solve for y. Right? If you substitute x equals 0, 2 to the 0 is 1, y equals 3. So it does that. You know, more than that, I mean, when we dealt with all the transformations before, you know, that was when you multiplied by a constant bigger than 1, that was called a stretch. Right? But we know now from an exponential function standpoint, if you've got a constant in front of there, that's the y-intercept. It has to be the y-intercept, right? y int 0, 3. Is the asymptote changed? No, the asymptote is still here. Is the domain changed? No. Is the range changed? No. Is it always increasing? You know, all that stuff is the same. So the only thing it does is a stretch, and it definitely changes the y-intercept. Okay, now exponential decay can be defined in a couple different ways. I think in your algebra 2, in algebra 2, exponential decay was when the a is less than 1. Like here, I've got a is 1/2. So for that reason, I'm calling it exponential decay. What does it look like the graph is doing? It's decreasing from left to right. And it's always decreasing. Would it pass a horizontal line test? Yeah, so it has an inverse. So this is decreasing. That doesn't change, right? Decreasing is different. The y-intercept is still the same. It still has an asymptote here. Y equals 0. The domain is still all reals. The range is still y greater than 0. Just the basic shape is changed. Now, if you look at 1/2 to the x, you know, using properties of exponents, you know, when you have a 2 in the denominator, right, then you could write that in the numerator with a negative exponent, right? That would be 2 to the negative 1 to the x, which is 2 to the negative x. And in this book, y equals 2 to the negative x is probably the way you're going to see decay. It's not going to be with a 1/2 there. It's going to be with a 2 there, but a negative exponent. So in fact, the a is still bigger than 1. It's like we never have a case where the a is less than 1. But sometimes they do use the a as less than 1. But it's not the way they're defining this now. Okay, right. Okay, now, and just the same kind of comparison. So I kept the 1/2 to the x on the slide, and I put a 1/3 to the x just to see, does it change much? Right? Does changing the base from 1/2 to 1/3 change much? Not much. Everything else is pretty much the same, right? So again, in generalities, if I was sketching it, it wouldn't matter to me much whether it was a 1/2 or a 1/3. I'd still sketch the same graph, right? So. Okay. And I meant to say on the, I think it was 2 slides ago, because believe me, some of you are going to make this mistake. when you multiply by a constant, 3 times 2 to the x, do not multiply 3 times 2 and get 6 to the x. It does not work that way, right? The 3 is not being raised to a power. So don't make that mistake. That's on the order of a silly mistake. Okay, now, kind of at this point, they kind of stick this in here. In the last version of this textbook, the solving equations in any way was something that was saved for section 4. And this one, they actually stuck this one in the first section. And I'm going to do it because I just haven't looked that hard into it. I'm not sure if they kind of underdo this in the 4th section, so I better cover it right now. Solving these kind of simple exponential equations is something you do by a property, which unfortunately goes by the name 1-to-1, which is what we called it when a function has an inverse, right? 1-to-1, passes horizontal line test. It's called the same thing. Okay. So when you solve a function, an exponential function using this 1-to-1 property, what you're trying to do is make both sides have the same base. And then because they have the same base, their exponents must be equal. So for example, I can write 8 as 2 raised to the 3rd power, right? So if I substitute 2 to the 3rd for 8, because they have the same base and it's an equation, right? The left equals the right. The exponents have to be equal. So you go right from this step because the bases are the same. You make an equation out of the exponents. And that's something you can just solve by normal algebra. Yeah. 2 to the 3rd equals 8. Right? 2 times 2 times 2 is 8. Okay, so solve, that becomes 4 equals 2x, x equals 2. Okay, how about on the right, on the problem on the right here? What do you think is the base that we're going to try to make both sides have? 27, you should recognize as being something raised to a power. 3 to the 3rd, right? And that's clearly 3 to the negative 1 because it's 1/3. So if I write it like 3 to the negative 1 for 1/3 to the negative x, and 3 to the 3rd on that side, I can simplify 3 to the negative 1 to the negative x by using properties of exponents. What's the operation when you raise a power to a power? What do you do with these two? You multiply them, right? So that would be 3 to the x equals 3 to the 3rd. Right, so using the 1-to-1 property, since the bases are the same, the exponents are the same. X equals 3. Right, so that only works when you've got exponentials where the base is some easily recognized power of, and it's almost always going to be 2 or 3. You know, maybe it could be 5. You know, they're not too many because the numbers get too big too fast when you start doing these as exponentials. So you should be able to recognize the numbers involved as being either 2 raised to a power or 3 raised to some power. Remember that if it's in the denominator, the way you deal with that is you use a negative exponent. Okay. Okay, so that kind of got stuck right in there. I'm not even sure why it was stuck exactly where it was, but now we'll go back to describe the transformations. You will have some problems which are solved with 1-to-1 property, and then there'll be some which just say describe. It does not even say the graph, right? It just says describe the transformation. So if you remember, we have done all kinds of transformations before. We've done it with absolute values and quadratics and I don't know what else, but the basic pattern is still the same, right? F of x equals a f of x, f of x minus h plus k, right? By adding or subtracting inside the function, it's a horizontal shift. Left means, plus means left, minus means right. Adding, subtracting after the function, vertical shift. Plus means up, minus means down. Multiplying by a constant is a vertical stretch or shrink. If the number's bigger than 1, it's a stretch. If the number's less than 1, it's a shrink. These are all just repeats of things we've done before. And what if that number in front happens to be negative? It flips over the x-axis, right? And how did you make it flip over the y-axis? You put a negative in front of the x. Okay, that would flip it across. So we didn't do much with that, but actually it's going to come up almost immediately here. Okay, so let's see. Or maybe okay. So what kind of shift do we expect this is? 4 to the x minus 2. Subtracting 2 inside the function. Describe the shift. 2 to the right. Okay, how about adding 3 after the function? That is up. Okay, now there's 2 different things going on in this one. The minus 3, that's the easy one, right? Okay, so that is the down. And that putting the negative in front of the x is flipping over the y-axis, right? So that is and using their language, right, we'll say reflect in y-axis. Oops. But just compare those 2 functions, right? Compare y equals 4 to the x and y equals 4 to the negative x. I mean, that is a reflect in the y-axis, right? But that's also the difference between growth and decay. I mean, that's exactly the difference between those 2 functions, right? One of them goes like this, and the other one is a reflection in the y-axis. It goes like that. Growth and decay. One is just a reflection across the y-axis of the other. Okay, let's see what I got next. I don't even remember. So this is I'm just showing this. I don't remember how many. There's not that much homework to do with this because actually this kind of, at this point, it kind of bores me. Okay, just all this shifting around of stuff. So notice what happens here. And letter A, which is this graph right here, I think. Right. You know, we're comparing. G of x is 3 to the x plus 1. Right? That's this graph right here. So what do we normally expect happens when we add 1 inside the function? It goes to the left 1, right? So it goes this way. So it takes this graph, and every point on this graph is 1 to the left of the point on that. By moving it to the left, like that, did it change the domain? Right? Domain is still all reals, unchanged. Did it change the asymptotes? I mean, if you take the whole thing and just move it that way, and you had a horizontal asymptote here to start, that's unchanged also, right? Asymptote. So did it change the range? No, it's still, you know, it goes down to the middle, but doesn't quite touch the x-axis, so the range is y greater than 0. Okay, now on this one, we're graphing 3 to the x minus 2, right? The minus 2 is coming after the function. And what kind of shift is that? That's down 2, right? So every point on this graph is 2 down from the graph above it. Okay, does that change the domain? Domain-wise, no, that's still the same, right? Domain, all reals. Did that change the asymptote? Yeah, it did. It moved the asymptote down, what do we say, 2, right? So the asymptote now is y equals negative 2, right? So what is the new range? right? The range is y greater than -2, right? Before it was y greater than 0, now it's y greater than -2. Because this graph goes all the way down. It doesn't quite get to the y equals -2 line, but it gets infinitely close. So a lot of times on these questions, on tests, students will say y is greater than or equal to -1. Like you just deal in whole numbers. But that's not what we're dealing with here, right? There's infinitely many points below y is -1 until you get to that graph. So it's incorrect to look at this and say the range starts here. It doesn't. It starts just above that line. It's got to be y greater than -2, right? It doesn't start there. There's all kinds of points in between. That's a fairly common mistake. Okay. All right. Where are we at? Okay. So now we're going to we had a couple different applications. First is called compound interest. Does anybody have a savings account or something like that? Okay, and you get some kind of annual interest rate, right? Compound interest is how you accumulate money when you invest your money in any kind of investment, but even a simple savings account, something like that. Now, let's say, and for just ease of calculations, let's say you got 12% annual interest rate, which nobody gets, okay? But let's say you got 12% annual interest rate. You don't get 12% calculated once a year. You get 12 divided by 12 calculated once per month. So at the end of the first month, they're going to give you 1% interest. And then after the end of the second month, they're going to give you 1% interest, not just on your original amount, but the original amount which was already increased by 1 compound interest. And so every month after that, you're getting the advantage of the fact that you were already given a fraction of that interest in prior compoundings. So what do you think that does to the total amount of money you're going to have? It makes it more, right? It doesn't double, but it makes it more. So compound interest is how investments work, all right? That's just how it works, right? The problems that we're going to do, we're going to end up with a couple of formulas. But basically, we're trying to calculate the amount of money that you'd have if you invest an amount, which that amount is called the principal, P-A-L, principal, right, in an account that earns an annual interest rate, right, which we refer with R, okay, and it's compounded N times per year, right, and it's in an investment for T years, right? That's what all these letters mean before we get into this, okay? When we're doing the compounding, if it says compounded annually, that means basically you're just getting the one time a year. That means your N is 1. If it says compounded semi-annually, that's N equals 2, right? If it's quarterly, N equals 4. If it's monthly, N equals 12. And if it's daily, N equals 365 compoundings. Yeah. No. Continuous compounding has its own formula. We're going to get to that in a minute. I mean, compound interest is, it's a fact of life. There's a famous supposed quote from Einstein saying something like, compound interest is the most powerful force in the world, or something like that. You can Google it, right? Here's a biography of Einstein. He didn't say that, probably. I mean, he's the guy that basically, the theory of relativity leads to the nuclear bomb. So I think he knows something about powerful things. And if he said it, he was joking. Okay, it wasn't real. Okay, so compound interest. Okay, so this is how it works again. Right? If you invest a principal amount, right, before you've done any compoundings, how much money do you have? You got that amount. That's all you've got. The first time you compound it, you've got that amount of money, plus you've got a little bit more money. You've got that amount of money multiplied by the interest rate divided by the number of compoundings. So for example, like I gave you an example, right, if you had a 12% interest rate and then you divide it by 12, then you're getting 1%. So 1% times whatever that principal was. So we're going to write that like the P, the principal, is being multiplied by 1 plus R over N. After the first compounding, that's how much you're going to have, right? Because you're distributing this, right? The P times 1 gives you your original money back. The P times R over N gives you the added interest that you earned. Okay. Now, at the second compounding, right, you're going to get a little bit more, which is going to turn out to be, and I didn't write every little detail in here, but it'll be the principal times 1 plus R over N squared. Okay? And the next time you'll get, for the third compounding, you can calculate how much you got by the principal times 1 plus R over N to the third. So you see the pattern? For the number of compoundings that you've got, it's going to be P times 1 plus R over N raised to the number of compoundings. Now, if you're compounding so many times per year and for so many years, then the total compoundings is going to be N times T, right? The number of compoundings times the number of years. Now, number of compoundings per year times the number of years, that tells you that exponent right there. Okay, so that leads to a formula, which is, I think I got it on the next slide. Well, we're going to get to it here. That's where we get this formula from. But we'll go back to that in a minute. Okay, but as Pierce brought up, there's actually another formula that we use, which is pretty interesting. If I start with that formula, right, P times 1 plus R over N times T, and if I substitute, okay, for no other reason because I know where I'm going with this, if I substitute N equals M times R, okay, so I know what the R is, and I know what the N is. The M is just a constant that I'm putting in there, okay, so I wouldn't worry too much, but I could say that when the N increases, the M increases. They vary directly, like we learned about variations, right? One goes up, the other goes up. Now, because I substitute N equals MR, that means right there in that formula, I put in an MR. And in the exponent, in place of the N, I put an MR. Okay, now inside the parentheses, now you've got an R in the numerator and R in the denominator. They cancel. So you just got 1 over M. And then properties of exponents-wise, again, I can take that M from the MRT and write it like this. 1 plus 1 over M raised to the M, and then all of that is being raised to the RT power. Okay, slightly different version of the same formula, just with N equals MR. Now, let's see what happens, as we let the number of compoundings, N or M, increase, what happens to that function right there? So let me put that in the calculator and see. Clear. Y equals clear. So 1 parentheses, 1 plus 1 divided by X, and the parentheses raised to the X. Does that look right? Yep. Okay, and I'm gonna for my calculator, I am gonna set my table set to ask. Set. Now I'm gonna go to my table. Come on. I don't know why it's doing that. I don't know why. That's okay. It doesn't matter. Let me put in 1, okay? So if I put in X equals 1, Y equals 2. Let me put in 10. Oh, that was not 10. Okay, now I get 2.59. Let me put in 100. 2.7048. How about 1,000? What we're looking at here is the end behavior of that one term. What is going on is a number of compoundings increases. And you could see it's starting to converge around a number. One more. Right? 2.7181. Let's see if I go one more. 100,000. 2.7183. I mean, it's definitely convergence. It's like a horizontal asymptote on our graph. That's what the end behavior is. Well, that number is actually a particular number, which is, it's actually as 1 over 1 plus x to the x, as the x increases, approaches an irrational number, e. Okay, that irrational number, it's kind of like pi, and we use it in science. You use it all the time. Okay, all the time, and it's a decimal. It does as a decimal. It doesn't terminate or repeat because it's irrational. The basic value of it, 2.71828 ... It's going to go on forever. That is called the natural base. Right, the natural base. And if you look at your calculator, you know, you find the pi, right? Pi is, put it over here. Right. Pi is on the hat, is on the caret, whatever you call it over here. You can't see it on my screen, but it's right there. That's where the pi is. Look on the button right down below it. There's your E. Right. So E is a character. It's used all the time in math and science. So it has its own button on your calculator. And there's actually, if you go to the other side, we will learn about ln later in the chapter. That's the natural logarithm, meaning the logarithm which has E as its base. And so right above that button, you see e to the x. Right. So E. It's a very important number. So if you remember in our formula here, we've just said as we let the number of compoundings increase beyond a certain point, this number in here is all going to be E. So that leads to a different formula, at least it looks different, for what they call continuous compounding. You know, continuous compounding, I'm not really aware of whether anybody gets continuous compounding or whether it's just like telling you, you know, this is like the limiting value of what you might get by increasing the number of compoundings. But when you replace that whole middle thing that I had on the other side with an E, then the formula is A, the amount, equals P, the principal, times E, the natural base, raised to the RT power, right? What's the one letter that you're not seeing that you saw up here? The N, because we don't have a finite number of compoundings anymore to plug in, right? There's less to plug in this formula than there is here. Remember that E is a constant. It's not another variable. It's a constant. Okay. So there's our two formulas. If we have to calculate compoundings for a finite number of compoundings, we use the first formula. If we're going to do it for continuous compoundings, we use the second formula. Let me know. You good, Mason? Okay. You know, I could add one thing. Okay. When you do the R, make sure your interest rate is a decimal. So like if it says 6%, annual interest rate becomes 0.06. Right? In the formula, you need to enter in the decimal. Yes. NT. This is NT, this is RT. Okay. So let's do an example of that. You invest $6,000 at an annual interest rate of 4%. Find the balance after 7 years if it's compounded quarterly, monthly, continuously. Okay. Find the balance. Okay. What's the balance? Which letter is that? In that formula, what letter is representing the balance? The A. Right. What is the 6,000 that you invested at the beginning? P, right? What is the 4%? Right. In fact, I'll say R is 0.04. And what is that? That's the T. Okay, and so we're going to do this 3 times, right? Well, we're going to do it 2 times before we get to the last one, which we change formulas. But for the first one, N equals quarterly, 4. And for the second one, N equals 12. Okay, so let's do that. A equals 6,000 times 1 plus 0.04 divided by 4 raised to the NT. So that is 4 times 7. So A equals 6,000 times 1.01 raised to the 28th power. And I'm going to just do it in this calculator, clear. 6,000 times 1.01 raised to the 28th. 7,927. And how many decimal places do you think I should show? It's money, right? So probably going to do 2%. 74 is 0.745, so that becomes 0.75. Right, so what will change in our formula now that we have N equals 12? The N goes to 12, everything else is the same. So A equals 6,000 times 1. I'm gonna leave it like 1 plus 0.04 divided by 12, so I don't lose anything. And now it's 12 times 7. So let's see, 6,000 times parentheses 1 plus 0.04 divided by 12 raised to the 12 times 7, 84. 7,935.08. $7,935.08. Okay, now, am I going to use the same formula for the last one? No, because it's continuous compounding, we got to use the PERT formula, right? For this one, we're going to use A equals PE to the RT. A equals principal 6,000 E to the 0.04 times 7. So put that in your calculator, 6,000. And again, you got an E button there. You could either do the E, right, which is on the divide symbol, or you could use the E to the X, which is above the LM. It doesn't matter. That'll just pop you right into the exponent. 0.04 times 7. I'm getting 7,938.78. Now, if I had to do, yeah. Annual interest rate. What's the question? R is annual interest rate. 4%, 0.04. Okay. If I had to do a lot of calculations with that, I'd probably just put it in the calculator as a function. And then, you know, if I'm trying to like vary the number of compoundings, then that'll be my variable. And then I just look in the table for each one. I mean, you could even do it. I'm, you know, honestly a big fan of doing things like this, right? In this particular problem, go like this. Second, quit. Okay, I can go. 6,000. Store. Alpha. Where's our P? P is on the 8. Right? What else do we know? We have R is 0.04. 0.04. Store. Alpha. R is on the X over here. What else can we put in? I want the T, 7. 7, store. And alpha T is on the 4. Oh, I did something wrong there. Oh, I didn't. I guess I 7 store. Alpha 4. There we go. Right, and now the only things left are the amount, which is going to be our function, will be A as a function of the number of compoundings, which will be our X. So now I'm going to come up here and do alpha P. Again, that's 8 parentheses 1 plus alpha R, which was on the divide. That was wrong. Alpha, I think I got the wrong. It's on the times. Yep. Right, divided by the X, which is the number of compoundings. Right. And then I'm going to raise that all to the NT power. The N is the X. And then it's alpha T. Say again? 4. And then when I go to my table of values, you know, let me do it a second. Let's put that back to auto. Right? One compounding, right? There's annual, there's semi-annual, there's quarterly. You know, you can just go to your table and look them all up and not do like a whole bunch of individual calculations. There's our annual, monthly, right? And you could even just like scroll down until it gets way down there, and then that'll be your continuous. You know, when X gets big enough, that's what it's going to anyways. Okay, so compound interest, that's one application of exponential functions. And then I'm going to read through this one because we can't do much like the kind of problems that we're going to end up doing at the end of the chapter will have to do with solving these equations. At this point, we don't know how to solve these equations. Only one way we know how to solve them, that's that one-to-one property. None of this stuff is going to lend itself to one-to-one. All we can really do now is evaluate them. I mean, that's all this thing is asking you to do. Plug in for the variable and see what you get. So you shouldn't look at a thing like this like another word problem you're not even going to try. Read it. It's not that hard, right? So this one, it's practical. It's a real-world story, right? In 1986, a nuclear reactor accident occurred at Chernobyl in what was then the Soviet Union. The explosion spread highly toxic radioactive chemicals such as plutonium over 239 Pu over hundreds of square miles, and the government evacuated the city and the surrounding area. To see why the city is now uninhabited, consider this model, right? Where this is the amount that's left based on there was the principal amount. It's 1/2, which is telling us what kind of exponential function is this, because the a is less than 1. It's a decay, and then it's being raised to the t over 24,100 power. So, which represents the amount of plutonium after t years. Sketch the graph of the function over the interval t equals 0 to t equals 100,000, where t equals 0 represents 1986. How much of the 10 pounds will remain in the year 2017? Well, how would you figure just that? How would you figure how much is left in 2017? You're going to plug in for t, right? Are you plugging in 2017? What are you going to plug in? T equals 0 is 1986. So what does that make 2017? Yeah. 2017 minus 1986, which is 31. Right? So if you want to know how much is left in 2017, put in a 31 right there. P equals 10 times 1/2 raised to the 31 over 24,100. Okay. Anybody do it? Fine. 10 times 0.5 at 31 divided by 24,100. 9.99. So how much is it lost? It started at 10, and now it's 9.99. It's like all there still. Nothing has really gone away. Okay. Now, if you were going to graph this thing, right, it says sketch the graph of this function over the interval t equals 0 to t equals 100,000. So you would have to, in your calculator, it would go from 0 to 100,000. And what would you use as the y scale? What's the maximum amount? 10, right? It said it starts at 10 and goes down from there. So it's a lot easier in some of those problems where we got to figure out how high to make the graph. In this one, you don't. It's going to go from 0 to 10. So you'll have a problem that's just like that. Okay.